Welcome to Unit 8, Section 2, Simplifying Radicals. After this lesson, you'll be able to use the product rule for radicals, the quotient rule for radicals, simplify products and quotients of radicals with different indexes, use the Pythagorean theorem, and then use the distance formula. So, the product rule for radicals is if the nth root of a and the nth root of b are real numbers, and n is a natural number, then the nth root of a times the nth root of b is equal to the nth root of ab. That is, the product of two nth roots is the nth root of the product. So, let's go through some problems. It'll be easier to understand. So here we have the square root of 5 times the square root of 13. We can just basically, and I'll write this extra step out, though we don't need to, 5 times 13. This is equal to the square root of 65. So, this is pretty easy just to go ahead and do. Square root of 7 times xy is the square root of 7xy. This also works for other roots, right? So these are both cube roots. So this would be the cubed root of 14. Over here, this would be the sixth root of 8 times 2 is 16. R squared times R cubed is R to the fifth. Over here I have fifth root multiplying by fifth root, so my answer is going to be the fifth root of 9 times 8 is 72. X times x is x squared. Y squared times y squared is y to the fourth. This last one here, since this is a square root and this is a cube root, is already simplified. It cannot be any more simplified. Okay, so your answer would just be square root of 7 cubed root of 5. Now the quotient rule for radicals. If the nth root of a and the nth root of b are real numbers and b does not equal 0 and n is a natural number, then the nth root of a over b is equal to the nth root of a over the nth root of b. Okay, so the nth rule of a quotient is the quotient of nth roots. As we did before, we'll just go through problems and that'll make more sense. Okay, so we're going to simplify these. So the square root, this becomes equal to the square root of 100 over the square root of 81. Well, the square 100 being a perfect square, that's the equal to 10, and the square root of 81 is equal to 9. Okay, so for the square root of 11 over the square root of 25, take those apart. And we don't know what the square root of 11 is, but that's okay, because the square root of 25 is 5, and we're simplified. Over here, cubed root. So this process is the same. We have the cubed root of 18 over the cubed root of 125. And as a quick reminder, we can easily find the cube root of 125 by using the math key and going to the number 4. And there's our cube root, and just putting our number in. And that's 5. Over here we have y to the 8th over y to the over 16. So this will be the square root of y to the 8th over the square root of 16. Keeping in mind the square root, the index is 2, so 8 divided by 2 is y to the 4th, and the square root of 16 is 4. Okay, over here we just go through the same process. Negative cubed root of x squared over cubed root of r to the 12th. I can't do anything with the numerator, so that'll just stay the negative. This will be negative cubed root of x squared. But because 12 divides evenly by 3, I have r to the 4th. So the conditions for a simplified radical are: the radicand has no factor raised to a power greater than or equal to the index. The radicand has no fractions. No denominator contains a radical. And exponents in the radicand and the index of the radical have no common factors. Okay, so we're going to take these and work on these. So these are pretty basic problems, right? This is similar to the problem we did yesterday, where I can look at this and say this is equal to the square root of 16 times the square root of 2. So that's 4 times the square root of 2. The perfect square 16 goes into 32. Perfect square that goes into 300 would be 100 times the square root of 3. So that would just simplify to 10 square root of 3. The factors of 35 are 1 and 35 and 5 and 7. Therefore, this is already simplified. So we've got the square root of 35. Okay, the cube root, that perfect cube that goes into 54 is the cubed root of 27, right? We've seen this one a few times. And that goes into 54 2 times. So now we could take the cube root of 27 as 3 square root of 2. If you look here, 243, we may want to come over and factor this into the product of primes. So let's do that. 2 doesn't go in, but 3 does 81 times, which is 3 times 27, which is 3 times 9, which is 3 times 3. So this is equal to the 4th root of 3 to the 4th times the 4th root of 3. And as we just learned earlier, this is the absolute value of 3, which is 3. So we have 3 times the 4th root of 3. Okay, now we're going to get a little more in depth with this. And what we want to do is we want to break it into pieces. So the first thing I'm going to do is break the square root of 25. Then the biggest even number that can go, can be taken out of 7 is 6, right? So this is the square root of p to the 6th, and then the square root of p. So this will make sense in a moment. Square root of 25 is, oops, not 25, but 5. The square root of p to the 6th is p cubed, and this will be the square root of p. Okay. So perfect squares that go into 72. Well, that's equal to the square root of 36 times the square root of 2, right? And then I would have y cubed has a y squared in it, so I'm going to do a y squared here, and then another y, and then square root of x. So the square root of 36 is 6. Square root of y squared is y. And then under my radical sign, 2xy. So I'm going to take the cubed root of negative 27, right? So we're looking for 3's, right? The cubed root of y to the 6th, right? Factors of 3. And then this would be the cubed root of y. Over here then I'd have the cubed root of x cubed, and then the cubed root of x squared, and then last the cubed root of z to the sixth. So the cubed root of negative 27 is negative 3. Cubed root of, let's go in descending order, cubed root of x would be x, right? And you can cross these out like this as you work through. The cubed root of y to the sixth is y squared, right? Just divide 6 by 3. And we would do the same thing with z squared. And then under the radical sign of cubed root, we'd have x squared y. Right? We took care of all these. Okay? Alright, so negative fourth root, right? So 32 is 2 to the fifth. So we'd want 2 to the fourth, and then another square root of 2. A to the fourth can come out, because that's a to the fourth times a. And then we would have b to the sixth times b to get b to the seventh. So negative square root of 2 to the fourth is 16. Square root of 16 is 4. Right? So we got rid of that. Square root of a to the fourth is a squared. Square root of b to the sixth is b cubed. What do we have left? Square root of 2ab. Okay, so if you remember, okay, so we were going to divide. We were told, I was telling you earlier, hey, you can divide this into this, right? Well, this also can come back the other way and divide the index. All right, so whichever one's bigger, you're going to divide. So 12 divided by 3. So this will become the fourth root of 2. And to show you that those are equivalent, right? If I take my math button here and I go down to number 5, and I can just say the 12th root of 2, and then put my exponent in there, cubed, hit enter, right? That's equal to this value here. If I do my math button again and I go down to number 5 and I put the fourth root of 2, I get identical values. Okay. So we can see that those are equivalent. All right. So keeping that in mind for future problems that we are going to be working on. All right, so the sixth root of t squared is equivalent to the cubed root of t, because 2 goes into 6 3 times. Okay, so if m is an integer, n and k are natural numbers, and all indicated roots exist, then the kn root of a to the km is equal to the nth root of a to the m. Okay, which is pretty much what we just did. But now we're going to take this, and I'm going to show you this, but I'm not going to throw this on any tests or anything like that, but I think it's important. So we know that this is 5 to the 1/2 power. And this is 4 to the 1/3 power. And if we can get these to be equivalent values on the index, we can combine them. So 5 to the 1/2 power, all right, if I look and if I were going to work with halves and thirds and add them together, they got to be converted to sixths. So this would be 5 to the 3/6 power. This would be equal to 4 to the 2/6 power. So now we go back to radical form. So this is equal to the sixth root of 5 cubed, and this would be equal to the sixth root of 4 squared. So now I can go ahead and just combine this sixth root of 125, and this would be the sixth root of 16. Alright, so now we're going to take these and we can combine them. The sixth root of 125, that represents the square root of 5, times the sixth root of 16, that represents the cube root of 4, and when we multiply them we get the sixth root of 2000. Alright, moving on. The Pythagorean formula, or the theorem. So if C is the length of the longest side of a right triangle, and A and B are lengths of shorter sides, then C squared equals A squared plus B squared. The longest side is the hypotenuse. Two shorter sides are the legs of the triangle. Keeping in mind, sometimes they won't have this 90 degrees. They'll have a box. All right. And the hypotenuse is always opposite, right, of the 90 degree angle. Okay. So let's do some problems where we solve a right triangle, find a length. All right. So the first thing we have to figure out is, what length are we looking at here? Well, as we stated just a moment ago, this is the hypotenuse right here, right? It's across from this 90 degree angle, right? There's our 90 degree angle, and across from it is the hypotenuse. So we can say with pretty certain sense of certainty that that's our formula. A squared plus 14 squared equals C squared. So 8 squared is 64, and 14 squared, well, you just take your calculator, and 14 squared here is 196. So 64 plus 196 equals C squared. So the square root of, oh, excuse me, I'm jumping the gun here. So this is C squared. So this would be 260 is equal to C squared. So I can take the square root of each side here, right? So we would have this is equal to C, okay? 260, we can go ahead and factor this out. So let's do that. 260, that's 2 times 130, which is 2 times 65, which is 5 times 13. Okay, so we've got a pair here that we can work with. So this would be the square root of 4 times square root of 65, or 2 square root of 65 is equal to C, and that would be your final answer. Okay. Over here, which one's our hypotenuse? Well, it's opposite here, so 6 is our hypotenuse. So we would have B squared plus 4 squared equals 6 squared. So B squared plus 16 equals 36. Subtract 16 from each side, I get B squared is equal to 20. Take the square root of each side, I get B is equal to the square root of 20, which is equal to the square root of 4 times the square root of 5. That's kind of a goofy looking square root symbol. Square root of 4 is 2. Square root of 5, I don't know. But there's my answer, 2 square root of 5. All right, now we're going to talk about the distance formula, which is really nothing more than the Pythagorean theorem in reverse. And I'm just going to come over here to the side and explain how this works. So if we have a Cartesian plane here, okay, and I've got a couple of points, let's say here and here, right? And I can take those points and connect them with a lovely dot, or excuse me, line, not dot. Jeez, oh Pete. Yeah, that'll work right there. So this would be the line we'd be looking for, this distance from here to here. The other thing we can do, though, is I can take a line and drop it down here, right, and create a right triangle. So there's this, and then we would come here, and we would draw this. So here's our right triangle. Okay, now we would figure this out by using Pythagorean theorem. Okay, so we don't know this distance, but I would know these coordinates. So this might be x sub 1 and y sub 1, and this would be x sub 2, y sub 2. The coordinates right here would be this x value, x sub 1, and the y value, which would be y sub 2. So if I wanted to calculate this distance here, right, I would take and say, well, x sub 2 minus x sub 1. All right. If I were to do it over here, I would look at the y values because it's the changes in y. So I would say, let's say y sub 1 minus y sub 2. Now, you're going to come back over here and look at this and say, well, wait, you've got y sub 1 minus y sub 2, right? Why is that not the same? Well, the order doesn't matter because we're squaring it. So if I end up with a negative value in here, once I square it, I'm going to end up with a positive. Okay? Just like taking positive 2 and square it, I get 4. Negative 2 and square it, I get positive 4. Okay? So let's do a problem and see how easy this really is. Okay, so the distance here is equal to the square root, and I always just put these squares and a plus, right, in this. Okay, so 2 minus 5, just do my x's. I just do them left to right. Negative 1 minus 3. So this is equal to the square root. 2 minus 5 is negative 3 squared plus negative 4 squared, right? Negative 1 minus 3, okay? Negative 3 squared, positive 9. Negative 4 squared, 16. I get the square root of 25, which is 5. Nice. Okay, let's do this one here. Same process. Negative 3 minus 0. 2 minus negative 4. Okay, so this is equal to negative 3 squared plus 2 minus negative 4 is 6 squared. So I end up with the square root of 9 plus 36, which is equal to the square root of 45. The only perfect square that goes into 45 is 9. So my final answer is 3 square root of 5. So that concludes our lesson today, because there's nothing underneath there. Make it a great day. Peace.